Good evening and welcome to this class. Today I think is what, 20th or 19th? 20th of February, and today is supposed to be strike, but we are not affected. I don't know what strike is all about. They always strike. Anyway, we were talking about MSI circuits, medium scale integrated circuits, and we talked about the advantages of MSI over SSI. The four mantras are reliability, cost, size and power consumption. Actually, I can also include one more, speed, because when the circuit is very small, speed is high. So, you can maybe add the fifth point: reliability, cost, size, power consumption, speed. All these advantages from MSI to LSI will be much better. From LSI to VLSI it is better, like that it goes. And last class we saw exhaustively multiplexers, what a multiplexer is, what are the different types of multiplexers, how to build a multiplexer tree for higher order multiplexers. We saw some applications. More importantly, we saw how to make Boolean realization using multiplexers. That is a very interesting concept. Today we will take some other MSIs. One of the most frequently used, very frequently used MSI is called decoder. Actually, encoder and decoder go together. Multiplexer demux, encoder decoder, like that. What is a decoder? Decoder has, it decodes codes. Suppose I have 3 bits, I0, I1, I2 as 3 inputs. I will call them A, B, C, and there are 8 combinations possible. I0, I1, I2 can be 0, 0, 0, 0, 0, 1, etc., 1, 1, 1. So, I can decode this into 8 combinations: O0, output 0, output 1, I stands for input, O stands for output, O2, O7. Here we have a code of 3 bits, 8 values, only one value is true at a given time, and that value corresponds to that value, there will be an output. Supposing the value is, if this is LSB or this is MSB, this is LSB, O2 is 0, 1, 0, output 0 is 0, 0, 0, 0, 0, 1, 0, 1, 0, and this is 1, 1, 1. So, if I give 0, 1, 0 to these 3 inputs, output O2 will be triggered and I can use it if I want to. This is something like, we talked about ASCII codes, 7 bits expanding into 127 possible combinations. Each letter has a code, each alphabet has, each uppercase letter has a code, lowercase, each numeral, each special symbol. Like that, here also I can have 8 codes, and each of these codes will result in one application, one output. This will be useful, is very useful thing by implementing again logic functions. Suppose I have a function of ABC which is given by min terms, let us say 2, 4, 6, 7, anything arbitrarily. I can draw a truth table, I can draw a corner map, I can write a logic function, and I can draw using gates. Instead, now I will say this M2, M4, M6, M7, M2 corresponds to 0, 1, 0, M4 is 1, 0, 0, M6 is 0, 1, 1, 0, M7 is 1, 1, 1. So, if I have these outputs 2, 4, 6, 7, give them all into an OR gate, this is my output F, that is the logic function I want to implement, consisting of 4 variables, 4 terms. The terms are 2, 4, 6, 7, which is 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0 and 1, 1, 1. Corresponding outputs I take, tie them together in OR gate. That means this function is true if this is true, or this is true, or this is true, or this is true. That is what a truth table is all about. So, you can, other words, you can say the decoder is a hardware truth table in hardware. This is very useful, very useful. We can also have the opposite, because many times the outputs are not high. There are 2 types of outputs possible in logic gates, like an AND and an NAND. AND has output high, NAND has output low. This is A and B, this is A and B bar. So, many times we would like to have negative output for many reasons. I can also have a decoder whose outputs are negative rather than positive. Suppose I have a same decoder with same 3 inputs. But the outputs are O0 bar, output like AB bar. Like AB bar here, I have O0 bar. How do I know it is a bar? Because of this bubble here. Bubble is always a symbol for inversion. Inverter also has a bubble, right? It's an inverter. So, this bubble tells you it is an output negative or output low. Negative is not true. We normally use it in common usage. It is low output, high output, 0 output, 1 output, 0 volts, 5 volts. That is how it is. Then O0, O1 0, O1 bar, O2 bar, O7 bar. Now I want to have a logic implementation of the same F is equal to sigma m, that is min terms 2, 4, 6, 7. Min terms 2, 4, 6, 7 are to be present in our final output. Now, this is M2 plus M4 plus no plus is R, or M6 or M7. What is F bar? De Morgan. Demorganize it. M2 bar and M4 bar. See, demorganizing, the variable gets complemented, and becomes or becomes and. this F bar. Now F would be complement of this, F will be the complement of this, that is what this will be, M2, M4, M6, M7. So, this is same as the negative of M2 which is O2 bar, inverse of M4 which is O4 bar, inverse of M6 which is M6 bar, inverse of M7 which is M7 bar. So, O2, O3 bar, O4 bar, O5, O6 bar. So, I will take O2 bar, O4 bar, O6 bar, O7 bar, which is same as M2 bar, M4 bar, M6 bar, M7 bar, but I need a NAND gate output, not an OR gate output. So, this will be put through a NAND gate, this MSF. So, now I have two ways of implementing a given logic function which is ABC M246, decoder with positive high outputs, decoder with negative or low outputs. Decoder with high outputs, we simply tie using an OR gate all the min terms that you need. Decoder with low outputs, you choose the terms, tie them together with an NAND gate. That is all there is. So, this is very convenient, I can use it this way or that way, sum of products, product of sum, NAND output, NOR output, I mean NAND output and output, whatever is required we can do that. That is very interesting. This is called a 3 to 8 multiplexer, 3 to 8 demux, I mean decoder. 3 inputs, 8 outputs, 3 to 8. We can have 2 to 4, 1 to 2 actually, nobody uses this, 2 to 4, 3 to 8, 4 to 16, 5 to 32, decoders are possible. Again like a multiplexer we can have a decoder trees, bigger decoders we can get using smaller decoders in a chain, in a tree. In a tree like structure, like we had lower multiplexers forming part of a bigger multiplexer chain, I can have low order decoders forming a chain of higher order decoders. One other thing is these decoders are used very much in design of memory circuits and all that. Sometimes when you have this, I do not want any of them, there is ABC may be given to more than one decoder, but I want output of this and not this, supposing I want to be selective. I can have different decoders with the same inputs, but I want some of them to be active, some of them not active. So, we have what are known as enabled signals. I have not introduced this concept till now. Today I am introducing this concept, enabled signals. In digital electronics, everywhere we have these enabled signals. What is an enabled signal? An enabled signal is, if I want to enable this, if I want this circuit to work as I have written here, that means I should enable it. If I do not want this output to be defined by this, Instead of cutting the, you see I have this different decoders, I want one to act at a given time, I cannot physically remove them, the others. The encoders or decoders which you do not want to work for a given at a given time, we can't remove them physically. Somebody has a question there? We cannot remove them physically, we cannot disconnect them physically, so we use enabled signals. Enabled signal tells you if you enable it, it will work as required, as defined. If you disable them, it will not work. Output will have, there will be no output. As if it is a wire connected without any value, 0 or 1, it will just be hanging. So these enabled signals, there are several enabled signals possible. Generally they put it like this, EN. EN stands for enable. If I want this circuit to work as I defined, I should put a connector 1 here. 1 is either 5 volts, 3.3 volts, whatever is your 1 level. If I do not put it, if I make it as 0 volts, if the enable instead of 1 I make 0, then this does not work. You may have inputs, no output will come correspondingly. Correspond to the inputs you have, you cannot define the outputs. There are more than one enables possible. In the 3 to 8 decoder, normally 3 enables are there. These are all only different types of ICs manufactured by different manufacturers. So whatever I say may be true for one. Whenever you are going to use an IC in your design, on your laboratory experiment, you have to look at the data sheet. Who is the manufacturer of this IC? Is it National Semiconductor? Is it Texas Instruments? Is it Motorola? Nowadays everything is available on website. Earlier there used to be big books, data sheet, data book, data book, data book. Today you go to the website of National Semiconductors and go to decoders, they will tell you all the decoders possible. They will give you the circuit diagram, they will tell you how much voltage you can apply maximum, how much voltage minimum, what is the current it takes, everything will be there. You should always consult a data sheet of a particular IC before you use it in any practical application or in the laboratory. You make it as a habit. A lot of people do not do that. I want you to make it as a habit. Before you use anything, at home when you buy a TV set, new TV, you read the instruction manual, right? Otherwise you do not know how to use. So the same concept will apply to the laboratory also. Now what you do is, so there are generally three enables, 2 active enables, active low enables, 1 active high enable. This is normally, it is not a universal rule. It need not be true. It is one possibility. But do not take my word for it. Go to the website, go to the data sheet of that website, and then see for yourself what are the enable signals required, how much you should apply 1 or 0. In this case, if this IC has to work as per the requirement of 3 inputs and 8 outputs, active low, I have to put a 0 here, 0 here and a 1 here. 0 is 0 volts or whatever is the low voltage for your IC, 1 is 5 volts or whatever is the high voltage. It can be 3.3 and 0, 1.2 and 0, whatever. These are called enabled signals. They generally call them G1A, G1B and G2. As I said, there is only one explanation, one particular IC I have in mind, it's called 74138. All the manufacturers, see one advantage of this IC is, there may be different manufacturers, they have standardized on the number. The 74138 is the 3 to 8 decoder with active low outputs. whether Texas Instrument makes it, National Semiconductor makes it, Motorola makes it, or any other semiconductor manufacturer makes it, they will use generally, it is not a rule again. You cannot go to court on this. 74138 is normally given for that, and normally these are 3 enables, 2 are active low enables, 1 is active high. Why do you want 3 enables? Because sometimes you may use one of them when required and other 2 may be permanently connected. All that later on we will see all those uses, why we need so many. Right now I am only discussing the ICs available. Okay. Like MUX and DMUX, you have encoders and decoders. Now we are talking about decoders. What is the complement of a decoder? Encoder. What is an encoder? We have several inputs and a fewer outputs. Here fewer inputs, several outputs, decoder. The complement, the reverse is several inputs, small number of outputs. So, we will talk about encoders. There also we have this enables, but I am not going to do this every time. I told you what enable is. It is up to you to read them up. Encoders, reverse of decoder is encoder. So, I will have several inputs I0, I1, I7, that is 3 to 8, 8 to 3 encoder. So, 8 bits is what you do the coding, you know. When I have a 8-bit stream 01100, I can use it as a 3-bit value. An 8-bit can be compressed into 3 bits, it is called encoding. 3 bits to be expanded into 8 bits is called decoding, that is all. Now, 3 outputs O0, O1, O2. Here also all these positive outputs or low outputs, high outputs, enable, everything is there. I am not going to discuss everyone in detail, we already talked about it. So, now what is going to happen? If you give one input I0, this will become 0, 0, 0. If you give I1, it becomes 0, 0, 1. If you give I2, becomes 0, I am sorry, this is LSB, no 0, right? 0, 1, 0, and if you give I7, 1, 1, 1. From the output you can see what is the input combination which is active. Only one input is active. For that input, what is the output? This is encoding process. Here also you can have active low, active high, enable everything. These things you please read up. Here there is a problem which is not found in encoders, I mean decoders. The problem is what happens if more than one input is given at the same time. Suppose I give I1 and I6 at the same time. I1 corresponds to this, I6 corresponds to how does the encoder behave? How does the encoder know what it should give as output? How do you as a user know what is happening? That is, there is a scheme called priority scheme. Priority encoders, you define the priority. You say a higher input will always get the precedence over a lower input. So, I1 and I6 are coming at the same time. It is your definition that I6 will be encoded, not I1. You can have the reverse. If I have two inputs, I0, I1 and I6, I will always make sure that the lower one will get the output, higher one will be ignored. You can define it. So let us say it is a higher priority encoder, it is called priority encoder. We will always make sure that the higher of the two inputs or highest of the many inputs will see the output, rest of them will be ignored. So it will be like this. So I have this table, priority encoder as table, I0, I1, I2, I7, output will be O0, O1, O2. Now if none of them is present, then I will have 0, 0. No output. If I0 is present, what is I0 code? Again 0, 0, 0. There is a confusion here. If I1 is present, irrespective of I1 is present or not, that is called don't care. We have talked about don't care condition earlier. Whether I1 is present or not present, I0 is present or not present, I1 will be decoded, encoded as 0, 0, 1. Similarly, if I2 is present, I0 may be present, may not be present. I1 may be present, may not be present. Output will correspond to I2, which is 0, 1, 0. When I7 is present, whatever happens to the other inputs, output will be 1, 1, 1. This is called a priority encoder. The one with a higher priority will give the output. The priority is not always the higher one. We can also have a lower one. But normally we put it a higher one. Only one question here. I am going to ask this question to anyone who can answer. Put your hand up. I0, nothing, no input is present, I have 0, 0, 0. If I0 is present, rest of them are absent, then also I have 0, 0, 0. How do I distinguish between the two? Is the question clear? The question is, when I0, I1, I2, everything is absent, I have 0, 0, 0 as the output. If I1 is present, I0 is present and rest of them are absent, that is I0 is 1, all others are 0, then also I have 0, 0, 0. These are two different conditions, I have the same output. Do you understand this question? How am I going to resolve this conflict? Anyone who has an answer can put your hand up, and then I will request Kannan to unmute you. Anyone? Aruna Engineering College. If any of you has an answer, please raise your hand. I will request Kannan to unmute you. Somebody has it.
Subhashish has got the answer.
Yeah, you can unmute him.
I am unmuting Subhashish, sir. One moment,
Yes.
sir. I will unmute him. Subhashish, you are unmuted. You can go ahead.
Sir, if we use enable signal.
Subhashish, please go ahead.
Hello?
I use enable signal. Yeah, you said something like that, enable, right? How does it work?
Sir, if we use sir, if we the means when all the inputs are 0, if we disable that, then we'll get 0 output.
Yeah.
And when we put I0 equals to 1, we enable that IC.
You mean the other times IC is disabled, you mean? Is that what you are saying?
Sir, Subhashish wants to answer, sir.
Yeah, he has said that. So, yeah, he is already answering.
All right, sir.
Yeah. Yeah, that is
Sir,
more
it
or
is
less
correct.
right. That is more or less right. So, but what we do is we provide an extra output called D output. The same as what you are saying in a slightly different way. Slightly different. Same answer, rather same concept. So, when this combination alone D will be 0, all other combinations D will be 1. So, looking at this D signal output, this enable is an input whereas this is an output, that is the only difference. What you said is right, but instead of enable as an input signal which you use in decoder, we will use D as an output. This output D will be 0 if no input is present, and for all other input combinations 1 to 7 D will be 1. From there you can know. So, not only you should look at these 3 values O0, O1, O2, you should also look at D. More or less same answer that you said, but it is slightly different, modified. Good.
அந்த work நடக்கவே நடக்காது. அதான் விபினுக்கு தெரிஞ்சதுன்னா சொல்லு. சொல்லி எல்லாம் எடுத்துட்டு சொல்லு. இப்ப சார்ட்ட போய் பாப்போம். நான் அந்த கிளாஸ் முடிஞ்சோன வருவேன். எடுத்துட்டு சொல்லு. சார்ட்ட போய் பார்க்க சொல்லு. நான் சொல்லி
Somebody is talking very nicely in Tamil. Who is this person?
I have no, sir. It's Kongu Engineering College.
Kungu.
With great difficulty they got connected, but they started shouting, so I muted them.
Kongu.
Ama, sir.
Kongu Engineering College in Coimbatore. Yes, near Coimbatore. Why are they taking a lot of Tamil? Very good. I think I should switch out to Tamil medium.
No, sir, there are so many people from the north and from the west.
No, I was now joking, sir. Don't worry. I will not do that.
Yes, yes.
Don't think I will do it. But it is very nice to see. Kongu Tamil is supposed to be very sweet. They say, I don't know. I am not from Kongu, so I don't know. So Kongu Tamil is supposed to be very nice. So somebody talked in Kongu Tamil. I was really impressed. Okay. Any questions? Everybody unmuted again. Muted again. Okay. We are talking about decoders, encoders, priority encoders. There is one other small concept which I have to tell now. I could have told any time. There is no need I have to tell now. You can also tell later. But I thought today I will do that. When I was, see, I usually, even though the topic is not new to me, I have been teaching this for so many years. Before coming to class, I just organize my thoughts, usually. And if there is any problem I have to work out, I will write it down because I don't want to make a mess. Usually I write down problems, even though I can write down and sometimes it may become wrong, you know. So when I was organizing the thought, I suddenly thought I should talk about something called 3-state buffer. Have you heard of this? 3-state buffers. I will talk about 3-state buffer for a minute before moving on to other MSIs. So the second MSI we have seen. First MSI is multiplexer and its combination, different variations. Second MSI is decoder, encoder, all that is 1. I am just putting it as 1. So first MSI is multiplexer and its variations. Second MSI is encoders or decoders and its variations. Now we will go on with the MSIs some more. Before that I want to talk about what is known as a 3-state buffer. It's a very useful concept. Whatever we are saying is useful in design. We are now looking at, you see, we are talking about like these children playing with blocks. You have to understand the blocks before you can build. Like why children, even adults, when you build a house, you should have the components. You should understand each one of them and then put them together to make a house. Like that in digital right now we are doing, what we are doing is, we are looking at various building blocks. When the system is built, our subsystem is built, our module is built, we will use some of these or many of these. So the 3-state buffer is some concept which is very useful. Some people call it tri-state buffer, but usually it should be called a 3-state buffer. There is a copyright problem with tri-state buffer. Tri-state buffer belongs to National Semiconductors. They do not like that to be used by others. So others should use it as 3-state buffers. Okay. 3-state buffer is, suppose I will give you a simple idea. Suppose I have a full adder. Why full adder? I will say adder, because we are going to define full adder, half adder and all later on. I have an adder, I want to add two numbers. One number is called A, other number is called B, or I will call is E. First number is E, and we have sum and carry. Second number can be either A or B or C or D, we do not know, one of them. Sometimes I want to add A and E, sometimes B and E, sometimes C and E and all that. One number is fixed, other number is selected from a different number groups. So I connect all of them together. I do not know which one, and every time I can't be changing my connections. I cannot be snapping wires and soldering them. I cannot be changing everything in hardware. So I am going to give all my numbers A, B, C and D into this, the second input. Second input of the adder is C for carry, do not get confused with this C, sum and carry. A, B, C, D are all present. I will use one of them to add with E and get the sum and carry. But I do not want to put them all at the same time because it will be confusing to the adder. If all of them appear as the second input of the adder does not know which one to take. There is a conflict. It is called a bus contention. Something like going to a bus, same bus, you cannot go to 4 different destinations. Somebody wants to go to place A, somebody wants to go to place B, somebody C and somebody D, all of them get into the bus. There will be a big fight between the people and the conductor and the driver. We do not want that. They say this bus will go here only, this bus will go only here, like that. So that is called bus contention. That bus is not same as this bus, but you can sort of think now. So what we do is, we give them through what are known as tri-state buffers, 3-state buffers. These are called buffers. Buffer is nothing but this is same as this, then in between logic. Both input and output are same for a buffer. Intermediately there is a logic. This logic will be controlled by another signal. we will call it enable signal. Each of these buffers, the 4 of them will have an enable signal. If the enable signal is active, if enable signal is given, A gets into the bus. If this is not active and this is active, B gets into this bus. If this is not active, this is active, C gets into the bus. This is not active, this is active, D gets into the bus. So we will add either A and E, or E and B, or E and C, or E and D, depending on which of these 4 enables is active high, is activated, others are active. You cannot activate more than one, then you are in trouble again. So I can have only one of the enables high, others all low. Whichever is high enable, that input will go into this, so it will be E and B sum. Why is it called three-state buffer? This is called three-state buffer. If enable is 0, this is output. I want to call it what? C, I will call it C. Not this C, don't confuse with this C and this C. This is another circuit, and in fact there is a buffer whose input is A and output is C. If enable is 1, high, 1 is high, 5 volts or 3 volts or 1.2 volts, whatever. C is same as A. What if enable is 0? It cannot be 0. C cannot be A bar. C is called Z or Z. Z stands for high impedance. What does it mean? High impedance, which means nothing will appear here. It's as if you have taken a pair of pliers and cut it. You don't physically do it. You don't physically do it. The wire doesn't exist, the wire doesn't take you anywhere. That's why it's called Z is high impedance. That means here I have 3 combinations. A is 0, C is 0, A is 1, C is 1, A is whatever, so A, C, Z is enable. A is 0, enable 1, C is 0. A is 1, enable 1, C is 1. A is whatever, 0 or 1, but enable is 0. Z. Z stands for high impedance, means as if the connection doesn't exist. It's very, very high impedance. That is what happens in an electric circuit. When you have very high impedance, what happens? No current flows, no voltage gets developed. That is why it is called high impedance. As if the state doesn't exist, as if the connection has been snapped. This is called 3-state buffers. Again you can have enable 0 or 1. So I can have an active high enable, active low enable. A enable, C, A is 0, enable 0, C is A, This is low, enable low level. I can have enable as high or low, does not matter. Such a signal is called enabled signal, and this is called 3-state buffers. It will be used all the time. Suppose I have a memory. My memory has several units: microprocessor, computer. I have several memory banks, same address lines. I want to read from here or here or here or here. Several memory banks with the same address locations. So address lines, data lines. You give the address, you get the data. That is what happens in a memory. But I want only one memory to be activated at a given time. I have addresses in all the 4 memories I am giving at the same time, but I want only one memory to respond. Suppose I want only this memory to respond, and this memory and this memory, we do not want it to respond. This address will be enabled, this will be disabled. So this can be EN1, it can be EN0, 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 or low level enable, this can be EN0, this can be 1, 1, 1. This is one simple application. Several applications exist. We will not talk about it now, but I want to tell you this reason for this. There is something called 3-state buffer. Why is it called 3-state? Usually we have a 0 or a 1 at the output of a gate. You have AND gate, 2 inputs, both are high, output is 1. One of them is high, the other is low, or both are low, output is 0. There are only 2 possibilities, output can be 0 or 1. There is a third possibility of Z. The possibility of Z or high impedance or no output occurs because enable has been disabled. That is why it is called a 3-state buffer. There are 3 variations possible in the output. Usually without enable signal or a non 3-state buffer or a non 3-state gate, only 2 outputs are possible, 0 or 1, high or low, low or high. I have a third possibility of Z or high impedance by using of an enabled extra signal called enable. That enable signal is activated, I get 1 or 0 as required. I can have an AND gate with an enabled signal, with both inputs are 1, the output will be 1. One of them is 0, the output will be 0. But if the same enabled signal is disabled, I may give 0, 0, 0, 1, 1, 1, 1, 0, the output will be Z, high impedance. It is a very important concept you should not forget. See all these things, multiplexer, demultiplexer, decoder, priority, enabling of all these signals, 3-state buffers, all these things are concepts which you will use later on in our design. Even if you do not use it in this course, you will use it in other courses in digital. This is only a first level course in digital, we are going to have other courses, computer organization, computer architecture, high level design, microprocessors, so many courses are there, these are required. So, I am giving you a basic course. I am giving you, exposing you to the various possibilities that exist in a digital design. Okay. So, I just made a deviation in the MSI representations after mux and its derivatives, after decoder and its derivatives. Before moving on further into, there are so many other MSIs I want to do, but I won't do all of them. You have to also read up. You watch my NPTEL lectures, or better still, take a book and read. Take a book. So, I am going to introduce only to a few of them. Next thing I am going to introduce is what is known as a parity generator.
After I got into my system, but it's some domain name .net. So how do I make sure that people are associated?
All of you remember what a parity is. Those of you who did not attend this course earlier, you should read it up. We talked about odd parity, even parity. We talked about what a parity is, how to add a parity bit, odd parity bit, even parity bit, all that. Remember that. I am not going to revisit that. If you are not here on that day, please read up. It is in my lectures, you can listen to the lecture. All the lectures are in website now, or read up, or Google it, do whatever. Now, I want to generate a parity. Earlier we talked about parity being required for error detection, 1-bit error detection. So, we talked about odd parity, where the total number of ones including the parity bit is odd, or even parity, where the total number of ones including the parity bit is even. So, we take a bit stream or 7 bits, 4 bits, 3 bits, 5 bits, 19 bits, count the number of ones. If the number of ones is even and I want an even parity, I do not put a parity bit, I put it as 0. If I count the number of bits and it comes as odd and I want an even parity, I add a 1 so that the total number of ones become even. So, total number of ones will remain either odd or even, depending on if it is an odd parity or even parity. So, if it is not there, you add 1. So, all that I am just sort of a summary of what I did earlier. So, supposing I have 4 bit, ABCD are 4 bits, or B0, B1, B2, B3. Bit number 0, bit number 1, bit number 2, bit number 3, and I want to generate a parity bit. Even parity bit. That means when I count the number of ones in these 4 strings, if it is odd, I put a 1 here, if it is even, I put a 0 here. That is all, as simple as that. There are 16 combinations, 0, 0, 0, 0. Please fill up this table, right hand side, left hand side, right hand side. What should be the parity bit for even parity bit for each of these 16 combinations? Quickly, you are not using your pen, do it very quickly. I will give it to you in a minute. Before that I want you to do it. So, this is called parity generator. We generate the parity bit. Earlier we talked about parity bit being used as an error detection mechanism. We defined parity and used it as error detection. Here I am going to generate the parity. If I want odd parity or even parity, in this case I want even parity. All you have to do is to count the number of ones and add a 1 if necessary to make it even. Zeros are even. 0 is considered even, so you do not add a bit. So it is 1, so I need a 1. This is 1, I need a 1. This is 1, 1, 2 already, so I do not need it. 1, so I need a 1. 2, I need a 0. 2, I need a 0. 3, I need a 1. 1, 0, 0. 3 ones, so I add a 1. 2 ones is 0. 1, 1, 0. This is my parity bit for this combination of 4 bits B0, B1, B2, B3. Now the question is, what circuit using gates or multiplexers or decoders or encoders, what circuit will generate this parity bit as required here? Design a circuit which will give you the parity requirement as it is, parity as required. What is the procedure? The truth table is given, output is given, all 16 combinations of truth table are given, corresponding outputs are given. How do you proceed? First step is to draw the corner map. This is truth table, translate into corner map. B3, B2, B1, B0, in the map you translate this into the map. So, this is 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0. This is the map. Now we have to simplify this map, get the logic function and implement it using gates that we are familiar with. I want to give you 2 minutes to come up with solutions for this. Once you are done, you raise your hand, I will request Mr. Kannan to unmute you. Please spend 2 minutes or 3 minutes, come up with the right answer for parity generator. Parity generator is G, we will call it, or PG. PG is what? As a function of B3, B2, B1, B0. Using this corner map, write down the Boolean expressions for this. Anyone who has finished, all you have to do is raise your hand. You might have finished now or you might have learned it earlier. Whichever way is fine with me. Some of you might have learned it earlier also, or they might have seen my NPTEL lecture. Yeah, you got the answer. Very good. Sir,
Sir, I'll unmute, sir. It's Dinesh. Dinesh is there. He'll tell you the answer. One moment, sir. Dinesh, please go ahead. You are unmuted.
Sir, it's need 3 XR gates, sir. That's enough.
what is the actual equation?
That's getting too much.
Huh?
That's getting too much, but simplify it in exclusive OR gate that it takes
I am not
3
hearing you
exclusive.
properly. Repeat it.
It's taking too much, sir, but simplify it. It takes 3 exclusive OR gates.
You have to give me the steps. I know the answer. That it needs 3 exclusive OR gates. Yes, sir. I know it. You have to tell me how it comes. Any book will give you this 3 exclusive OR solution. Yeah, somebody else raises the hand there. Who is that? Mr. Kannan, somebody else is raising there. Somebody else has raised the hand.
Sir, B0 XR B1 XR B2 XR B3.
Say it again.
B0 XR B1 XR B2 XR B3.
B0 XR, B1 XR, B2 XR. Is that right? Is that right? Is that what you said? Is that what you said?
Yes, sir. XR. It's not XNAR. XR.
I didn't put XNR. I put XR only. Come on, man. XR.
Okay, sir.
I never put XNOR there. I want to tell you how it comes. That is more important than the answer.
Sir, if you take the full adder,
Yes.
in the full adder, it is A XOR B XOR C in, sir.
Yes.
Similarly, this is also same case, sir.
Yeah, the pattern is same. This pattern is same. In XR we have only 2 rows. In full adder we have only 2 rows. So A, XR B, XR C. Here there are 4 rows, so we have one more variable. A, XR B, XR C, XR D. That is all right, man. I am asking you how do you
Okay,
get it? Okay, I will simply tell you how to do it very quickly. You see, these two form a XR of B0, B1. This is but B3, B2 bar, right? These are the first steps. Plus, this is XNOR of B3 bar B2. Then this one. This forms B3 B2 bar B1 XNOR B2 B1 XNOR B0. And finally these two form B3 B2 of B1 XR B0. This is the equation. This is the one which is reduced to this by taking common terms now. You have to say B0, B1. So B0, B1, B0, B1 into these two, and then this is this, oh this is which is exclusive OR. This is B3, B2 exclusive NOR. So these two form one set and these two form another set. So the whole combination will reduce to this. Same as full adder as we said, but we are not taught full adder yet. I am going from basics. Next topic I will add full adder, I will start with. Before that I am going to tell you something. Today another 10 minutes is there. Next class we will talk about adders, full adders, off adder, full adder, subtractor, BCD adder, which is very important, because in normal computers may add binary but we add decimal. So when you feed two decimal numbers in your calculator, each number is converted into what is known as a BCD. I told you what a BCD is already, but I will again tell you next time. So the BCD digit will be maintained, another BCD digit, and how do you connect two BCD numbers, how do you add two BCD numbers, we will see that. So next class will be adders, subtractors, BCD adders. But today we have some more time. I am going to give you an exercise which you have to do it at home, and I will explain to you the problem. Supposing I have this display like this, you see this display all over the place now, in clocks, in railway stations, in banks, tellers, wherever number comes, more than one digit of course, I am just giving you one digit. I can have 0 to 9 into this. 0 can be this without this, 1 is these two, 2 is this, 3 is this, 4 is this, is that right? 5, this is 5 actually. 4 is what? 4 is this, 5 is this, 6 is this, 7 is this, 8, 9, 10. All these 0 to 9 can be gotten using, how many segments are there? 7 segments. 1, 2, 3, 4, 5, 6, 7. So this is called segment A, B, C, D, E, F, G. It's called 7 segment display. Very, very commonly used nowadays. Wherever you go, your number is called. They will put a display. Of course, this is only one digit. You can have 2, 3, 4. You can have clocks 0 to 59, 0 to 59, 0 to 23. You can put dates, years, months, anything. As many displays as you want. But basically how does it work? We will take a single 7 segment display, find out how it works. Now, sometimes there is a point also here. Suppose it is a decimal number, they call it DP. decimal point. After G they have dp. Sometimes, for example, you want to have this number 32.7, I want that point. So sometimes dp is also used. So how do you do that? I am going to explain to you how to do it, but you have to do it yourself. This is a homework problem. You will also give it in the next assignment sheet, but before that you can try it at home. So I am going to represent 0 to 9. 0 to 9 is binary 0, this is 0 decimal number. That is all I need. 10 to rest of the 6 combinations. With 4 bits I can have 16 combinations. I have used only 10 of them, 0 to 9. Rest of the combinations 10, 11, 12, 13, 14, 15 are not going to be used. Zero, 1. These are not used combinations for a decimal display. For a decimal display we want only 0 to 9, 10, 11, 12, 13, 14 possible also with 4 bits are not going to be used. These are don't cares. Outputs. We already defined what is a don't care output, how to use it beneficially to simplify the logic. We did that. Now, for 0, what are the segments to be displayed? A, B, C, D, E, F, G. And you want decimal point, you can put dp if you want. That is optional. For 0, I want A, B, C, D, E, F. A, B, C, D, E, F. G need not be present. I will leave decimal point now. If you want, you can add it. For 1, B and C. And like that I can write. For 8, everything has to be on. For 8 will be so I wanted to fill this table, which is the truth table for a 7 segment display. Write the truth table. For a 7 segment display starting from 0 to 9, 9 will be what? Depends on whether you want 9 this way or this way. Let us say you want it this way. A, B, C, D, F, G. A, B, C, D. That is assuming you want 9 like this. If you do not want this, A, B, C, F, G. Anyway, And your advantage, great advantage, I am going to put all don't cares here. They can be 0 or 1, 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 0. Don't cares can be used to advantage in simplifying logic. We have seen that already. Now take each display, each segment at a time. There are 4 inputs B3, B2, B1, B0 and one output A. So for example, I can draw the map for A as map for segment A. Go to finish this. A 2 will be, only A will be writing. So A will be 1 for 2, 3 A will be 1, 4 A will not be there, 5 A will be there, 6 A will be there if you write like this, 7 A will be there, 8 A will be there, 9 A will be there. So A will be 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, rest of them are don't cares. Don't cares can be used as 1 or 0 depending on our advantage for simplification. This is the map for segment A. So now I can simplify A as you write prime applicant for A and that will be my logic for A, segment A. Then you can do it for segment B, C, D, E, F, G. Then you can have individual circuits designed for A segment, B segment, C segment, D segment, E segment, F segment, G segment. And then you can make a decoder. This is available as a single IC. I want you to know how it is done. But you can go and buy in the market a 7 segment display decoder. They will give you one small thing. Maybe cost about, I don't know, 12 rupees, 10 rupees, even less than that. So in this case A would be B3 B1, this one will be B2 B0, this will be B2 bar B0 bar. Like that you write for B, C, G and draw the circuit for each one of them. In fact, you can do one step further by identifying terms which are common for this. Supposing the same term appears here, I don't have to build 2 circuits. I can use the same term here as well as here. This is very important IC and use extensively, you know everywhere. I have a clock in front of me here. This display is there. You go wherever today we have this displays. Traffic signal, it tells you how long you should wait. Everywhere you see this today. As I said, you don't build it now, it is available, but you should know, you are a designer. If you are the user like everybody else, what is the difference between a digital designer and a user? We are digital designers. You got a good job and design ICs and then make a lot of money and become rich and famous, right? Okay. See, today it's 5:30 now. Any questions? I will unmute all of you. Couple of minutes for questions. If you have no questions, see you next Monday. Unmute, sir. Kanan. Mr. Kanan. Any questions? Anybody? Yes, sir. Ayush. Tell me.
Sir.
Unmuted? Please unmute everybody. It's over.
Yes, sir.
Ayush. Tell me, Ayush.
Sir, in the Karnaugh map,
Yes.
sir, in the K map of this 7-segment display,
Each segment separately.
sir, why we have used that don't care digits, that
You
cross one in that?
You don't have to. If it's useful, use it. See, I am having this 8 ones. If I have this 4 don't cares, I have this 8 ones. Similarly, if I have this 1, in order to use this 1, I use all these 8, these 2 ones. That is all. I am using it because it is useful to me. I don't have to. Do you find anywhere I have used it unnecessarily? Tell me, I will change it.
No, sir, but can we use it as it does not do any harm, sort of, in the circuit?
It does not do harm, it reduces your circuit. Now I have only one term for this, only one variable B2, B3, no gate. Only one variable B1, no gate.
Sir, in case if we have used that max terms,
Max terms, yes.
then also we can use them?
Yeah, max term also you can use don't cares. No problem.
Okay.
Don't cares are used
Okay.
as you like. It is to your advantage,
Okay,
you
sir.
use it. If it is not an advantage, don't use it. Don't waste your time
Okay, sir.
using it if it is not useful. Yes. Anybody else has a
Thanks, sir.
question? Anybody else? Yes, sir, he has a question. Hello? Ask me, everybody is unmuted now, I think. Sir, have you unmuted everybody?
Sir, in 3-state case, high impedance state you said.
Say it again slowly.
In 3-state case,
Ah.
high
Three-state
impedance state you
Huh?
high
Three-state
impedance state you said.
High impedance state, yes.
On that state, output will not come.
Output will not be there. There will be no 0, there will be no 1. It is as if it is an open circuit.
Logically we are disconnecting.
Logically we are discussing, not electrically. Electrically it is still connected, but logically it is not there. You don't recognize it.
Okay,
Like some
sir.
of you in the class, you are in the class but you don't listen to me. Like that. Yes, you don't use it. It is not there for all practical purposes. Yes, sir. Calcutta man. You are Calcutta, right? No. Say it again. Okay, tell. What is your question?
Sir, I was telling that what is the use of keeping high impedance? 0 output and no output means the same
Sir,
thing.
I have a gate. I need to connect it to my circuit. Every time I cannot disconnect, connect, solder, desolder, cut it, add it. It remains connected, but I don't want to recognize it. As if it is not there. It's an attachment which doesn't exist. That is why I need it. Supposing every time I disconnect and connect it, I don't need it, but it is too much work. And I won't even know which is required, which is not required. I gave you an example of adder, A, B, C, D. A may be there, B may be there, C may be there. That will be decided by somebody else. That will be decided by some other operation in a circuit, some other requirement of our algorithm. I won't know which is A or B or C or D is going to be connected, but I will enable that input ABCD which has to go in and rest will be disabled. Okay? Right.
Sir, but no output means 0 only, no sir.
No, that is what I want to tell you, sir. It is not zero output. Zero output and one output have specific current levels, voltage levels. Zero output is 0 volts, one output is 5 volts. Zero output and one output has different current levels. I don't want any of them. As I said, some of you in the class, you don't know I am here, you don't listen to me, you just sit there like that. Okay?
Okay,
Right.
sir.
Okay.
Thank you, sir.
Thank you. Anybody else? Arunai.
Hello,
Arunai,
sir.
you speak, talk. So many people are sitting. Ask me something.
Hello, sir.
Hello, who is that?
Arunai, please go ahead. Arunai, you had so many questions yesterday.
Yeah, who is that? Hello, sir,
Hello.
somebody said.
Sir.
Oh, one moment, sir. I'll see if they are unmuted. Yeah, Arunai is unmuted. Please go ahead.
Sir,
Yeah,
hear me, sir.
I'm hearing you.
Yeah, we can hear you.
Hello,
Please
sir.
increase your
Yes,
get
hello.
microphone closer.
Hello.
Hello.
Everything is
Hello, sir. In priority encoder,
priority encoder.
we are having two states. Both are having the same output conditions, no?
You are talking
explain
about
that,
first two inputs, first two
Yes,
combinations.
sir. We are not clear of what you're saying.
Okay.
Enable disable condition.
There are 8 input combinations and there are 8 outputs. For 8 input combinations, you have 0, 1, 2, etc. But no input combination and 0 input combination, where 0 is one of the input combinations. 0 to 7 are the 8 input combinations. For 0 input combination also I will have 0, 0, 0. For no input also I will have 0, 0, 0. These are not correct. I cannot have 2 possibilities in a given circuit. So I have an extra output called D. If the D is 0, that means no input is present. If D is 1, all other inputs are present. That means if all are zeros and that is I0, the first input is 0, output is 0, but D is 1. If no input is present, output is 0, D is also 0. That is all I am saying. Is it okay?
Yes, sir.
Thank you.
Yeah, sir, Kuldeep has a question, sir. Kuldeep.
Kuldeep. Go ahead, Kuldeep. Yeah.
Kuldeep, we are not hearing you. We're not hearing you, Kuldeep.
Yeah, he is not asked yet.
Did you mute?
Kuldeep.
No, we can't hear you, Kuldeep.
He has not talked yet. Come on, Kuldeep. You want to see me? I will come closer. I was sitting.
no, sir. You are visible.
No, I was sitting there.
You are visible to everyone.
Yeah. Tell me,
We are panning
Kuldeep.
the camera.
What is your question? Hello.
Kuldeep, no, Kuldeep. Kuldeep, please come for a audio video testing before you get into the class. All right. Okay. Anyone else, please?
Okay.
Yeah, Srikanth, you want? One moment. Sir, it is Srikanth. I am just unmuting him.
Okay, Srikanth. Who is Srikanth?
Srikanth, you are unmuted. Do you have any question? Srikanth?
No, Srikanth.
No, sir. No, Srikanth.
Okay. There's no more questions. We will stop here. That person has now. That is Kuldeep.
Yes, sir. Same Kuldeep. One moment, sir.
You have to ask me, sir, something.
Kuldeep, please go ahead.
He is not talking.
No, sir. He's talking. I think he's disabled his microphone, or there should be some problem with his mic. Sharanya, do you have anything to ask? I don't see anyone there in Sharanya.
Kuldeep, if you want, you can send me an email with your question. I will answer it in the next class.
Yeah. Please note down Professor's email ID. It is Srinis, SRINIS, SRINIS @iitm.ac.in. You have the details on the NPTEL website, and please go to the website, view the lecture, and come to the class. Our professor is writing it. Please note it down.
So Kuldeep, you asked, you can send me an email, I will answer it in the next class, because I would like to answer in the class so that others who also have similar questions can get the answer. You send me an email, I will not reply to it, but I will answer it in the next class. Okay? Have a good evening and a good weekend. See you next Monday.